Now, the next thing I want to do today to discuss the energy flow in the waveguide. First, I show you that the group velocity and actually the energy is transmitted at the group velocity. And now I am going to calculate the power transmitted in the waveguide. So it will transmit with the group velocity, and how we can calculate that the power transmission in the waveguide. The idea is simple. If the waves are transmitted by reflecting through the walls, we have E and H fields, we have Poynting vector, that is energy per second per area, and if we integrate this from the cross-section area, we will get energy per second, and that is the power. So I will show you that how we can calculate the transmitted power. Let me tell you again, this power is transmitted at the group velocity of the waveguide. And I will discuss the attenuation or extinction coefficient next time. So S Poynting vector is 1/2 E cross H complex conjugate. So that is a vector energy per second per area, and if I took the cross-section area of the waveguide and pointed some z direction, and if you integrate that through the cross-section area, I will get the transmitted power. But what I am going to get. So let us continue with the example with the Tm. Tm again. So let me show you what is S for Tm. 1/2. I can write this E transverse plus Ez. Since transverse, only we have H transverse. Okay, so this is the S Poynting vector for Tm, because we have only each H transverse because Bz is equal to 0. So what is this? That is equal to 1/2 E transverse cross H complex conjugate transverse 1/2 Ez cross H transverse complex conjugate. So from now on, I will use the information I have for the H transverse. What is H transverse? So let me go one step more. 1/2 E transverse cross H transverse, that is 1/wave impedance. So let me write the wave impedance here, and the leftover is Z cross E transverse complex conjugate, and the other 1/2 impedance of the wave, and Ez cross H transverse complex conjugate, that is Z cross E transverse complex conjugate. And what is this? That is equal to E dot E along Z minus E transverse dot Z along E transverse. What is the E transverse dot Ez? E transverse dot Ez. So let me write this in open. That is E transverse along Z minus E transverse dot Z along E transverse. What is this? 0, because the transverse direction of the field, electric field, is orthogonal to the Z. So that term will be the 0. And how about the second one? What is this? Ez dot E transverse is 0, orthogonal to each other, and you have Ez dot Ez, that is nothing but Ez along E transverse. So the pointing vector is the following. S is equal to 1/2 impedance times E transverse along the Z direction. What is E transverse for Tm? E transverse square. What is E transverse? E transverse is this quantity. So take the square of this. That is equal to K square. So that should be equal to I over gamma square K gradient of the transverse of Ez square along to Z. And the other term, 1/2 impedance, wave impedance, and what is Ez? Ez is Ez. And the E transverse, what is E transverse? E transverse is minus 1/gamma square K gradient of the transverse Ez. Close the parenthesis. So this is practically the pointing vector. So how can I calculate the power transmitted? What is the power transmitted? Power transmitted is S dot N dE, not say N, and say Z. On the average, power is transmitted along the Z. Okay? So choose any cross section and calculate that.
1/2 Z is repeated.
Yes. But practically this doesn't contribute to the power because this is along the transverse direction. If you take the scalar product with the Z, that will be 0. So no contribution, but that's good. So for Tm, power transmitted at the group velocity is equal to the following. So impedance is K over epsilon omega for Tm. So epsilon omega goes up, and this is K square, K cancel. We can get epsilon omega K square over K cancel out, epsilon omega K divided by, I have 2 here, and I have gamma to the 4th. And if I take the scalar product with the Z, this will be unity, and that should be 0. Okay, because this is in the transverse direction, no contribution, and you will get this integrated dE. So how do I integrate this? What is this actually? Gradient of the transverse is that dot product with the gradient of the transverse is that. So how do I integrate this? I will use the which you saw in the first part, Green's identity, Green's first identity. So at this point, I can erase the geometry part. So remember that the Green's first identity. So scalar function phi, Laplacian of psi, any scalar functions, gradient of phi, gradient of psi integrated through the volume is equal to surface integral of phi del psi over del n dA. This is the first part. Remember that identity. So this is 3-dimension, drops to the surface, okay? So that could be written in 2-dimension. In 2-dimension, this is area, this is length. Okay, you can drop the degree 1. That becomes, instead of volume and surface, you can have volume goes to area, surface goes to contour integral. So this is a closed surface in 3-dimensional, but if you drop the degree 1, the dl turns to be a contour integral. So how we can apply to this integral here? Is Ez is a scalar function? Yes. In this particular example, look at there. Can I say, instead of 2 different functions, can I say Ez? Of course I can say. So let's say this should be Ez. Let's say this should be Ez. Okay, you can do this. And what is this in that case? This part becomes to the what? This is Ez, and this is Laplacian of Ez, the second term. We have the plus area integral, and instead of surface, you have the contour integral, and that is Ez, del Ez over del n dl. Okay? If you say phi and psi is Ez, you can get this. And for the right-hand side, what is the value of the Ez at the contour? What is the contour here? What is the meaning of the contour? If you think about the waveguides, where is the contour? Yes, on yes, a line on the surface. And you know that from the boundary condition, if you go to any point on the yes, Ez should be 0. So this should be 0. And this term is the term we are looking, right? This you have the Z. And how about this? What can we say here? Do you know that what is Laplacian of Ez? Actually, this Laplacian is let me say that this is 3-dimensional. Let me take this at 2-dimensional. Okay, this is better. Otherwise, it's not good. Okay, this is okay in 3-dimensional. It's Laplacian, but in 2-dimensional, you should take the Laplacian in 2-dimensional transverse. And what is the Laplacian of the transverse of Ez? What is the Laplacian of transverse acting to the Ez? From wave equation, what is this? Yes, but you know this. I said you the Laplacian of E transverse plus gamma square is equal to acting on Ez or Bz have to be 0. Yes. Okay, this is the Laplacian in 2-dimension transverse, and gamma square was equal to what? mu epsilon omega square minus k square. Mu epsilon omega square minus k square. So basically you can write instead of this minus gamma square Ez. You are looking at this term is 0, so that integral is equal to the following. That goes to the other side is positive. We have a gamma square and gamma square is cancelled. So transmitted power will be epsilon omega over 2 gamma to the 4. That will be cancelled with the 1 of the gamma square. We have k, and what is left over? Ez square dE. Okay, so 1 of the gamma squares will cancel. Basically, transmitted power is the z component. It's related with the z component integrated with the what? Cross-sectional surface area of the waveguide. Cross-sectional surface area means this. This is the waveguide, and this is the cross-sectional area. We have to integrate through the area. You can do this exercise for the other mode also. You will get in that case Bz. There's a nice approach to calculation of the group velocity just using the energy transmission. So if you are interested in, just look at this. I calculated the group velocity using the dispersion relation, but if you look at the equation 853 in Jackson third equation, equation 853, the idea is the following. You have the power and you have the energy density per length, and you can calculate the group velocity in a different way. So look at this equation. That is very interesting and good. So I was doing in the previous years, but this year you can do it by yourself. Equation 8.53. That is the other way of calculating the group velocity. Energy is transmitted at the group velocity. So it is showing you that in a different approach. Now, after the Bayram, I will talk briefly about that attenuation coefficient, how we are going to calculate the attenuation coefficient, because these waves cannot go infinite. Some length it will decay because the conductors are perfect, not perfect. So we will study that, and we will start to study radiation.